Okay. So what is this, C9? Okay. All right, so I think it's number 4 and 5. All right, so 4 had us looking at the volume of a cube, right? And it told us a couple of things. So it said the volume is going to be a cube, so we know that the equation of a volume is going to be v equals x squared. You could have said length, you could have said side, whatever you wanted to name it. We were given that there is an error rate in the volume of plus or minus 27 inches cubed. So in this case, we said that the volume was going to be off. And then we asked, what is the error rate for the length of the side? So we're looking for dx. So don't assume that every number you're given, it gets plugged into the equation. Sometimes we can give you the opposite. So we had to make sure that we're using our units here. So now if I go back and I actually find the differential of this equation, right? It's dv equals 3x squared dx. Since I'm solving for dx, this is what I want to plug my values in. So I was given dv, but I don't know what dx is, or excuse me, I don't know what x is. But we were told in the problem that the desired volume, right, was 8,000 cubic inches. So if we plug volume into this equation, we can see that x needs to be 20 inches. So if you have a cube of size 20 inches, sorry, I'll like switch over here. I want to fix this. Okay, there we go. So if you have a volume of 8,000, that means the sides were 20. So now if we come down here, we've got plus or minus 27 cubic inches divided by 3 times 20 squared. So since 20 was in inches, right, this comes out in inches or units as desired. So you could have left it as plus or minus 27 over that. You could have changed that to 1,200. You could have simplified it, but that's the minimum that you needed to do. Any questions about that? So you're really going to use your units, but the process is the same, right? Label what you were given, find the model, write the differential, and then solve for whatever you're looking for, right? But if we tweak the error on one end of the problem, it's going to have effect on the other quantities in the problem. So the reverse side of this problem would be that we gave you which was the table problem, right? We give you an error on the side length measurement, and then you'd have had to figure out what the error of the volume turned out to be. Because you can see that if you measure each side the same, but each one's off by a little bit, when you cube it, it's going to compound those individual errors and, you know, give you a big discrepancy on the volume on the other end. All right, anybody that's ever tried to cook or bake, when you get something off, definitely affects the end product, right? So if you don't measure right on the going in the recipe.
Why is it about inches?
Because it was 20 inches and it got squared. Yeah. Because the units dx should come out in inches, because that's what dx was or x was measured in, right? So number 5 was the surface area, I think, for a horse. Such an odd thing to do, right? And remind me what the equation was. It was S equals
0.1
W to the 2/3.
Okay. So in this, we were given that dW is plus or minus 0.5 kilograms, and the weight of the horse, right, we were looking at was in kilograms. So they want you to figure out what the error in the surface area measurement is. So once again, right, error is just, we're going to use the differential for that, so we just take the derivative of this equation. So ds is 0.1 times 2/3 W to the negative 1/3 dW. And you just want to double check your units. We were given the error for the weight because it was in kilograms. We're looking for the change in surface area. So for this one, we just need to plug our value straight into the equation. So 0.1 times 2/3 times 280 to the negative 1/3 times plus or minus 0.5. And because we weren't given a unit of area, this should come out in area, so I would usually just default to like meters when you're not told exactly what's going on. But notice here, I saw a lot of people not doing this right in class today. Notice we're allowed to keep the plus or minus because it doesn't change the value of the problem, just the sign. But you got to put this in parentheses because if you don't, it looks like you're saying add or subtract 0.5, and that's not what we're saying. Multiply by positive 0.5 or multiply by negative 0.5. And just to give you an example, right, when we did this problem in class, if we wanted to do the error on both sides, we had to do a lot of calculations. But if I told you dx is, let's say, plus or minus 0.1 times 2, right? Well, then that just means this works out to be plus or minus 0.2. You just multiply, because 2 times 0.1 is 0.2. 2 times negative 0.1 is negative 0.2. So it's the same number. You just carry the plus and minus when you're multiplying. So this isn't meant to be super hard. Everybody was kind of making it way more complicated than it needed to be today. And so if you were to go in and calculate the error through brute force, like we did with the table problem, we were adding and subtracting things, and we had to do that for each individual thing. What we're doing now is we're multiplying by the error rate at the end of the derivative. So we're using the properties of derivatives to take advantage so we can just find the maximum error at any given point in time. And if we were doing a little bit more advanced problems, we would even say, all right, let's set the maximum error rate less than or equal to a number, and then you could solve the inequality and come back and find like what value would give you the, if you had a maximum error that you wanted to achieve. Yeah. All right, any other questions about this stuff from today? Just make a little bit more sense now? Okay, so this is just an application of differentials. I think when everybody was computing it out, it seemed really easy. You just tack a dr or a dx, and it seemed really basic, but those dr and ds's and dw, they actually mean something. It's the change in value, and so if we give you numbers for that, we can do some estimations. All right, what next? What do you want to talk about next? Gateway or related rates? Gateway? Okay, all right, yeah, that's coming up tomorrow, so let's do that first, then we'll jump back, because related rates isn't on the gateway. All right, so what about the gateway? No, I told you that'll be the second gateway for this unit. Because remember, every gateway repeat is the exact same topics. I just give you different problems. Okay.
What is the second gateway then?
It's in the syllabus. It'll be like, the date isn't fixed, but it'll be like toward the end of, like once we finish the unit, this is the first half of the unit, then we'll have another gateway on the second half of the unit.
Okay.
Yeah.
So will you go over the physics stuff today?
I don't think there's any, I mean, we can toward the end if you really want to talk about it, but yeah, but it's not going to be on tomorrow's gateway if you're stressed about that. Yeah. I actually think personally, one of the things I'd like to change up for the next incarnation of this is I'd actually like to move, well, it's when we're talking about rates of change, that's a natural application. I actually do think that application needs to be moved a little bit deeper into the unit because I think everybody's still just trying to learn derivatives.
The physics was just all over the place.
Yeah, it felt a little weird. I feel like now everybody would get it a little bit better than now that you're more comfortable taking derivatives and stuff.
Because like the related rates and then the physics stuff, like that's the stuff that I'm.
Okay, well, we're going to talk about the gateway and then we'll talk about that stuff. Okay. All right, so questions about the gateway?
Okay, so for your answer for number 2, cosine, I get like the first part, like the chain rule part, because you take the derivative and then everything inside, and then the derivative of the like ln thing, but then you get to the final, that's like.
Okay, so you're talking about this one?
X plus 2, yeah. That.
Okay.
Because I get like the first part, like 2 parts later, I don't get.
Okay, so I'm going to break this down. This was a like kind of like a triple chain rule, okay? So the outermost function was sine of u, where u was everything inside the sine function, okay? So then the derivative of this, right, is cosine of u. But then to do the derivative of this, we need another chain rule. So this guy, the outside function, let's call it ln of v, where the inside function was x plus 2 square root of x. So h prime, right, is 1 over v, and v prime, the square root of x is 1, and the square root of 2 root x is 1 over the square root of x, because it's 2x to the 1/2, and when I multiply the 2 by 1/2, I get 1, and then the negative 1/2 is what puts it in the denominator. So this times this gets me to here. So that's 1 over v times v prime. Then, to get the overall derivative, right, I multiply these two together. So it's cosine of u, which was all this stuff, times u prime. So it was like a triple chain rule. So I had to make sure that every time I took the derivative of what was outside, I was punning the inside and then working its way back out. So I feel like some people can do it when it's double, but if you add that third element, it just, people kind of fall apart on the third time, yeah. And so this is a method of staggering things down and breaking down each piece. You could just keep renaming your letters, and then I find it helps to indent, right? So you can kind of see that, and then you build it back up as you go back, yeah.
Just like, question for the future, are we going over U substitution in this class?
Mm-hmm.
Okay.
It's
Just
part
like
of it's
seeing
part
the
of
U
Unit D.
Bothers me.
So I'm the I prefer the letter U because U is a substitution variable to me, and that's really what you're doing here. You're
Yeah, I mean,
temporarily
you remind me of
right?
U sub, and I was
We
like,
are going to do that. I have a really logical, neat way of doing that too, of like
makes sense.
organizing
Intuition
things.
wasn't good
Yeah.
at it.
So that's why I prefer the letter U for the chain rule, because it's easy to mistake the chain rule and the quotient rule if you're using F and G for everything. And I think a lot of people, when they were doing their chain rule problems, I think that's why I got a lot of product rules as derivative of the first times derivative of the second, which wasn't right. I just like to switch up the letters, so it just kind of reminds me, if I'm in a hurry or stressed, that I'm doing a completely different formula at the end. And then, you know, F times U, you can kind of turn that into whatever thing you want. All right, what else?
The rules for differentiating logs.
Okay, yeah, let's review those. So, right, so exponentials right? So if we have a chain rule applied on, I'm just going to assume chain rule in all these cases, because if it's just e to the x, then the derivative of x is 1, right? So this is e to the u prime, right? But then, if it's a number a to the x, so like you guys had 2 to the x, well then it's a to the x natural log of a. So then if we have to apply chain rule to this, it's a to the u natural log of a, right, u prime. You just have to make sure to do the derivative of the inside on the very end of the problem. So here, the derivative of x is just 1. That's why you don't see that extra piece if we needed it. for logs, right, if we have natural log, well, it ends up just being u prime over u because it's 1 over u and then times the derivative of the inside, so we get u prime over u. If you want to take the derivative of log base a of x, well, it's 1 over x natural log of a. We actually derived those in class. So what I gave you on the quiz was log base a of u. We had an expression, x to the 5th. You could have either pulled that 5 down front, but it ended up being, right, u prime over u, right, natural log of a. So I just want you to see that these are all the same on each of these columns. It's just, I wanted you to make sure that you saw that the only thing that changes when you have the chain rule is that you have to tack on the derivative of the inside. So you get the u times u prime. And so the example over here, right, was we did e to the arc sine of 4x plus 1. So the derivative was e to the u. So you keep this the way it is, times the derivative of the inside, which was 1 over the square root of 1 minus this squared, and then we had to multiply times the derivative of the inside, so that's where the extra 4 came from. Over here, right, here we had a product rule, so it was 2 to the x natural log of 2 times sine x plus 2 to the x cosine x. And then when we took the derivative of this last piece, we said, well, we're right here. It's u prime over u natural log of a. So the derivative of the inside was 5x to the 4th over u natural log of the base. And that simplified to 5 over x ln 3, but you didn't have to do that. You could have just done it just like this. So any derivative I give you, you should be able to do chain rule on. But a lot of people just didn't know the derivatives. You could tell. They just didn't have them memorized.
The only derivative rules for the inverse trig functions are sine, cosine, and tangent that we need to know right
Yeah.
now, right?
Mm-hmm.
Okay.
Mm-hmm.
Could you show us how to do the other solution for the second one?
What do you mean for this one?
Yeah.
So, like, alternatively, right, you could have started, you could have just brought the 5 down front.
Okay.
So then when you get to this, the product rule here is exactly the same, but the derivative here, the 5 is on top, and it's just x ln of 3. And then here you can see x to the 4 is going to cancel one of those, and you're just left with x. Yeah. Faith?
So with the log base 3.
Uh-huh.
So that could be like log AG.
Yeah.
Okay.
Yeah.
So
Uh-huh.
when would it be log AX?
If it was log base 3 of x, right? Well, so right here, if you factor it down, now you've got log a of x, right? But I personally have always found that when I'm trying to memorize the derivatives, just knowing the most general form of it is fine. Because then here, well, your u is x, what's u prime? 1. You send a multiple, you get the same answer. So I find it's just better to know the u def of it, so you remember to tack on the u prime. Because once you learn chain rule, theoretically, they're all chain rule problems. It's just the derivative of the inside of a lot of those functions just happens to be 1, right? It's the same way we said back here, right? This is the form for any function a to the x. But e to the x is an a to the x. It's just ln of e is 1. That's why it disappears up here. But technically it's still there. It's ln of e and it just becomes 1, so it goes away. Yeah. So I think it helps if you kind of consolidate the list of things and you just kind of know how to work with it in general terms. Because if you're working with the u definition, the worst thing that'll happen is you end up taking the derivative of the inside and it's just 1. You know, it's not that big a deal. But I think algebraic property of logs stumps a lot of people. And I think if you're practicing logarithmic differentiation, that helps with the algebra because then you see how to simplify some of these problems a little bit better. They can't all be simplified, but some of them can be. Yeah.
Can you do the first problem?
You want me to do it using logarithmic
Yes,
differentiation? Yeah.
Because I wanted to do it, but I just didn't know how.
Yeah, and then somebody told me, well, in the time I would have taken me to figure it out, and I'm like, but it just took so much shorter to do it. Okay, so this is number 1. And I'm going to show you step by step how to do this using logarithmic differentiation, because this really was... I gave you one that was doable without it, but a lot easier if you used it. And that was kind of the option was, did you know you had this option? All right, so the first thing is I'm just going to set this equal to y. And then I'm going to take the natural log of both sides. So the natural log of y equals the natural log of all of this stuff. And I'm going to write out every step, but you didn't have to write every single one of these steps. I just want you to see every piece of the puzzle when we do this. All right, so the next thing you do after you take the natural log of both sides is you then expand this as far as you can go. So now we're just doing algebra. We haven't even started the derivative yet. So the natural log of the numerator minus the natural log of the denominator. Then I can expand the denominator so technically, right, it's natural log of this plus this, but this negative gets distributed because it's all in the denominator. So really you can just do the natural log of plus, plus, plus everything in the numerator, minus, minus, minus everything in the denominator. So then this becomes natural log of this. Then, before I take the derivative, I want to pull all my coefficients down front. Now I'm ready to take the derivative. And so we said, well, the derivative of the natural log of u is just u prime over u. So this is, right, y prime over y, or 1 over y dy dx, however you choose to write it. This is going to be 2 times 1 over 4x plus 1 times 4. So that's where the 8 came from. This is going to be 1 over 2x times u prime. Derivative of 2x is 2. Then this is 3 over x cubed plus 3 times 3x squared. So then we multiply everything by y, which is the original equation. And then 2 times 4 is 8. Those 2's canceled. And that's how I got 9x squared. So really, all I needed, right, were really those 3 lines. Some people, like once you've done this a bunch, you can go straight to the expanded form. If you've gone through those algebra steps on your homework, you could have taken me straight to there. And I had people that did take me straight to there, and I was like, yeah, that's right. They just knew the exponent was coming down. But if you needed to show those steps to get there, that's fine. But I would have taken just these last 3 lines. Would have been fine. And I actually did have a person use logarithmic differentiation almost perfectly. They just forgot the one little last step at the end for that e to the arc sine problem. And that was actually a really clever way. It took away one of the chain rules. So I can show you that. That would be another good example to show you on this. But
I think it was Gabriel because he forgot that.
I think he tried it. I think he got it, but I had somebody in my last class do it too, and he did a really close job with it. So this guy, which we saw a minute ago, was like a triple chain rule, right? If you did natural log of both sides of this, well, it wipes out the e and you just have to take the derivative of this now. So it actually took away a chain rule because natural log of e, right, is 1, and then the exponent came down front. So then this would have been 1 over y dy dx. This is 1 over the square root of 1 minus 4x plus 1 squared times 4. And then when you multiply both sides by y, that's where the original guy comes back. And so you get the exact same answer if you do logarithmic differentiation. So this one's an unusual one because the answer comes back exactly the way it would if you did the chain rule because the outermost function was e. So some of these kind of surprised me because the day we did these in class, all 3 of my classes just sort of like just gobbled it up. But you were able to look stuff up, I think, and we were deriving some stuff, but we did all those crazy chain rule problems. Everybody kind of, and I had everybody write on the board and stuff. So I don't know if that's maybe why people didn't look over it as much as they should have. They just thought they had it. But really to burn these derivatives, you have to memorize into your brain. You have to sit down and like really do some problems just to make sure. So WebWork's a good place for that. And some of the later sections in WebWork, when you're just calculating derivatives, are good because they've got all the other ones embedded in. All right, anything else about the quiz or gateway before we go on to related rates? The last problem, the implicit one? Yeah. So that was the implicit differentiation problem. So I think that was 3xy. Was it plus y cubed? Okay. So a lot of people forgot that the derivative of 5 was 0 on this one. That ate them up. All right. So this first term, right, we have a product rule. So the derivative of the first is just 3, right, times the second, and then plus the first term, and then the derivative of y is just 1 dy dx. The derivative of y cubed is 3y squared dy dx. And the derivative of 4x squared is 8x, and then 5 was 0. So now it's just an algebra problem. So everything with the dy stays on the left. Everything without a dy, x moves over to the right, and then you just divide it.
This is kind of a dumb question.
Mm-hmm.
Why would the dy dx go to 3x instead of 3y? I know that's like basic stuff.
Because that's where I took the derivative of y. It's when you take the derivative of anything with a y in it that you tack on the dy dx. So in the first term, I was taking the derivative of that expression and just multiplying by y. Here, I actually took the derivative of y. So anytime you take the derivative with something involving y, right? And then I had a couple people in multiple sections just start throwing dy dx's onto things that had y's in them, but never took a derivative at once during the whole problem. So the dy dx comes from the chain rule. It's the derivative of the outside function, and then the dy dx is your inside function.
I have like a question about linearization.
Uh-huh.
All that, but will that be Will like I be able to go over that with you next Monday?
Sure,
Okay,
yeah,
thank you.
yeah. Mm-hmm. All right, anything else on the gateway? I want to talk about some related rates, because I do want to show y'all those last two problems, and one of them there was like more than one method that you could have used, and I want to make sure that everybody sees that there's some kind of different routes to get to those answers. Because if you don't see things up front in those problems, it can make it kind of harder on the back end.
Are you gonna put this on six?
It'll be on YouTube. Okay, so I'm trying to remember. I think it was 3 and 4. So 3, if I remember, was the volume one of the, was that the dough problem? What was 3? No, in the actual in-class. Because not everybody got to finish that. And a lot of groups took different paths to that. So I think it was the cone. The salt one. Okay, that's what it was. All right, so that was number 3. So the salt cone. All right. So in this problem, right, we were told a couple of things. Y'all are going to have to remind me of some of these numbers. So if I remember correctly, we were told that the height was always 2/3 the radius. Is that how that went? Okay. So we had a pile of salt, right, that was forming a cone where no matter how much salt we poured in, right, we always had a height that was 2/3 of the radius. We also told you that the rate that the salt was flowing in, I believe was 3 inches, cubic inches? 3 cubic inches. And so it's a positive 3 because we're adding volume to the pile, okay? So what we're gonna really have here is a big fat round base with like a not so tall cone. So this was this guy. And then we asked you to find dH dt when R equaled 2. I think that was the right number, right? Okay. So there were 2 ways you could have approached this problem. So the first way is, let's assume for a minute that I just can't see the end game. I know that when I set up my relationship, so our model we were going to use was 1/3, right, pi r squared h. So that was the volume of a right circular cone. So let's just say for a minute that I really just couldn't see the forest for the trees, and so I just dove right into this problem and started working on it. So the first thing you would probably do is take the derivative with respect to time across here. So this is implicit differentiation, except now every variable gets a dt on it, but only when we take its derivative, just like with implicit differentiation. So the left side here is dv dt. This is a product rule. So I get the derivative of the first, 2/3 pi r dr dt times the second, which is h, plus the first term times the derivative of the second. And so since the derivative of h is just 1, I get just dH dt. So then what you want to do before you start doing algebra, because if you have to make any substitutions that aren't numbers, it can make you have to redo lines and lines of algebra if it ends up in the wrong spot of the problem. So the next thing you should really be doing is scanning the equation you have and figuring out, do you need to go look for anything else? So you were given dv dt, you were given r, we were not given dr dt, so that's something we need to find. We were not given h, so that's something we need to come up with. We have r, and we're looking for dH dt. So there's sort of 2 paths here, right? We can find h by simply plugging r into this equation. So if r equals 2, then h is 4/3, because it's just 2 times 2/3. So now we've got h. To get dr dt, Well, we have a second equation here, and we're told this ratio always holds. So that means their rates should be proportional as well. So I can just take the derivative of that equation with respect to t. So now, since I'm looking, and the other common mistake I saw in this one in class is everybody found dr dt, because the way we gave you the relationships, it was easier to replace the h's than it was the r's. So what you want to do here is we can go ahead and plug in the values we have, but I actually need to replace dr dt in terms of h rather than the other way around. So dh dt times 3/2 is dr dt. So all I did was multiply both sides by 3 and then divide both sides by 2. Also, r is 3/2 h. So I can come back to my equation, dv dt, and everywhere I have an r, I can replace it with 3/2 h. Everywhere I have a dr dt, I can replace it with 3/2 dh dt. Oh, this r shouldn't be squared, but it should be squared here. And so this actually simplifies quite nicely. This 2/3 and 3/2 just cancel each other right out. The 3's cancel and the 2's cancel. And so all I'm left with is 3/2 pi. There's my 3/2, there's my pi, and I have h times h. So I have h squared dh dt. Then I have 1/3, right, times 9/4, because this 3/2 gets squared. So it's 9/12 pi h squared dh dt. And I can cancel a 3. Out of this. So now I'll plug in some numbers. So 3 equals 3/2 pi. My h was 4/3, that gets squared. dh dt is what I'm looking for, plus 3/4 pi times 4/3 squared dh dt. I can factor a dh dt out on the right, and so I'm going to have 3 times 16 is 48, 2 times 9 is 18 pi, plus 3 times 16 is 48, 4 times 9 is 36 pi times dh dt, and then you just divide. So 3 divided by all of this is dh dt. And you could have consolidated that even further if you wanted to get a common denominator. So what you had to do here was, if you were only given information about one of the variables, we had to give you a second equation so you could then replace. Somebody find a mistake in my math? All right. So, alternatively, the second option with this problem. Has everybody got good to hear yet? Any questions? So it's 4 squared, 3 times 16 is 48, and 2 times 9 is 18. Yeah. All right, so alternatively, what we could have done in this question is we still would have started with the same model, everything to here that's in orange, okay? So everything I wrote in blue was one path, right? But what you could have done here was, once you've done enough of these, is, well, I know a drdt is going to come up, and I know a dhdt is going to come up, and I'm looking for dhdt, right? So, and it was really easy to find h from the r we were given. So what you could have done was you could have made the substitution at the beginning of the problem and reduced the variable at the beginning and said, well, I only want things in terms of h. So all you had to do there was say, well, v is 1/3 pi, r was 3/2 h, simplified, and gotten 9/4 h cubed. So then this is 9/12 pi h cubed. Now when you take the derivative, look what happens. dv over dt, 3 times 9 is 27, dh dt. So all you were looking for here was dh dt. So dv over dt times 12 over 27 pi is h squared dh dt. Plug in my h, which was 4/3. So then, oops, this is times. dv was 3 times 12 over 27 pi times 9 over 16 equals dh dt. So you could have reduced the variable at the beginning, and then you only would have had to deal with the h and the dh at the end. So that's just sort of something that will come with this little bit of experience, right? Every letter you see in these related rate problems, a d, that letter dt, should crop up in the problem. It's got to. So if we're asking you to look for things and we haven't given you enough up front, and that's why at the beginning of the problem, you should always call out all the quantities you have and list out what you're looking for, because it'll help set you on the path to find the right answer a little bit easier. So what about number 4, the distance to the point? That was sort of a similar problem. It wasn't quite as nasty as this one. So we asked you to find a point on the curve, and what was it, 2?
7 square root of 2x minus 1.
Oh, it was 7 square root of 2x
Minus 1.
minus 1, right? So we wanted you to find a point on this curve to the origin, right? And we wanted you to find the rate that the y coordinate was changing when we were at the point, what was it, 7 root 5?
Yeah.
Okay. So this is actually just the same problem we did before. So if you take the distance formula, and you square both sides, because we want an easy model to deal with. And so let's actually call this guy r, so that way when we square it, we don't have a d to deal with. So when you square both sides, right, you basically just get the Pythagorean theorem. And since the second point is always 0, 0, our model is just going to be x squared plus y squared. So I think they told us that dx dt in this problem, was it positive or negative 2? It was decreasing? Yeah, so it was -2, and we're looking, no, actually, I think DRDT was what they gave us in that problem. It was the distance to the origin was decreasing, so it was DRDT we were given. And we want to find DYDT. So if you're thinking about this one kind of the way we thought about the last one, I can already see